Welcome to our sneak peek for Switch 2.0. My name is Raymond Lacoste, and I am an instructor and author here at Live Learning, and I want you to join me right now as we peek into the advanced Switch 2.0 course. So what is Switch all about? It's about expanding your knowledge of the protocols, services, and features that you can deploy on your switches. Now, why would you want to do that? Well, you want to be able to build efficient, scalable, and more importantly, highly available Layer 2 switch networks. In today's day and age, always-on connectivity is important, and achieving your 5 nines of availability is extremely important for your entire infrastructure. So you want to be able to deploy all these different features, but you want to do so by following Cisco's enterprise campus architecture. And what is that? It's an architecture that's broken up into these different layers. We have our access layer, giving our end users connectivity, the distribution layer, which is going to aggregate our end users and their uplinks together, and then we have the core layer for throughput. So we're going to be looking at the different features, the different services, and the different protocols that we need to be able to deploy, number one, but two, manipulate and control the way we need them to be manipulated and controlled within our specific enterprise campus architecture. So one of the efficiency mechanisms that we can deploy is directly related to trunks. What does a trunk do? It allows us to pass traffic for multiple VLANs across a single physical link. However, do we really need to have every single VLAN cross that particular trunk link? Think about broadcast traffic for a second. If broadcast traffic arrives on the switch, what does the switch do to it? It floods it out all ports except the port it came in on. So that means that if the VLAN is allowed on that trunk link, the broadcast will go on that trunk link. Meaning that we have an inefficient use of our links when there is nobody out that particular link or further on down the road going down that link that needs that particular broadcast. So we need to be able to control that, and we can do so manually on a trunk by trunk basis by using the switch port trunk allowed command. Look at this topology. And I want you to focus specifically on DSW1 and ASW1. You notice how they're connected together? Gigabit 1/0/1 is connected up to gig 0/1 between ASW1 and DSW1. Which VLAN is connected to ASW1? Just VLAN 10. I don't see any other users connected to ASW1 that are in any other VLAN. So therefore, in reality, between DSW1 and ASW1 on that trunk link, we only need VLAN 10 traffic to cross. Because right now, by default, all VLANs are going to be allowed on the trunk link, and we can verify that with the show interface trunk command. When I look at this output, we'll see that all VLANs are allowed on the link going down ASW1. But in reality, only the ones that are created or known by the switch within the management domain will be allowed. So here we can see these are the VLANs that DSW1 knows about, but those are also all the ones that are going to be allowed to go across the link. So let's say right now PC4 sends a broadcast. It arrives at DSW1, it will be sent down to ASW1. So even though PC4 is in VLAN 20, that doesn't matter. The fact of the matter is VLAN 20 is allowed across this trunk link. So ASW1 will get that broadcast, but then it has nobody to send it to. So that's a waste of our resources, reducing the overall efficiency of our Layer 2 infrastructure. So we'll go to global configuration mode, interface gigabit Ethernet 1/0/1, and then we'll use the command switch port, trunk, allowed, VLAN, and we're just going to say 10 in this example. And after doing so, when we analyze the output of show interface trunk, we can now see that only VLAN 10 is going to be allowed across that particular trunk link. Now we'd have to do the same thing on ASW1 because we don't need to send anything but VLAN 10 across that trunk link. But the key here is now if PC4 sends the broadcast, it arrives at DSW1, DSW1's not going to forward that down to ASW1. So we are reducing the amount of non-necessary traffic that has to be flowing across various trunk links within our infrastructure. Now No switch course is complete without a discussion on spanning tree protocol. However, in Switch 2.0, we dive deep into spanning tree protocol. We analyze spanning tree protocol, rapid spanning tree protocol, multiple spanning tree protocol, so different flavors of it. But more importantly, you really need to understand how spanning tree protocol works, how its algorithm makes the decision on who the root bridge is, who the root ports are, who the designated ports are, and ultimately, when it's all said and done, which ports are going to be blocked within the topology. Now, spanning tree protocol is known by all as simply the protocol that prevents layer 2 loops. And I agree with that statement. However, at this level, we need to understand more about spanning tree protocol. For example, it's not just about preventing layer 2 loops. Think about what spanning tree protocol does. It ultimately determines the layer 2 forwarding path through your infrastructure based on how it makes its decisions. For example, in this case, we have our root bridge right here. And then from there, this is going to be a designated port, designated port, designated port. This is a root port. This is going to be a designated port. This one's designated. This is blocking. This is root. This is going to be blocking, and this one's going to be root. Now, if you don't know how I figured that out, you'll definitely want to join us in the Switch 2.0 course, so you can fully understand how spanning tree makes this decision. But ultimately, in the end, what else did spanning tree do? It has determined how traffic will be forwarded through our network. Because if this PC here, PC1, wants to talk to this PC over here, PC4, how is the traffic forwarded? It's going to be forwarded this way. So spanning tree protocol chooses that for us. What if spanning tree protocol has chosen a suboptimal path based on our layout, based on our topology, based on how the algorithms run? We need to be able to manipulate that decision that spanning tree protocol has made. And the only way you'll do that is by fully understanding how the algorithm makes its decisions. So that way there you can modify who the root bridge is, which ultimately modifies root ports, designated ports, and the block ports. And as a result of all that, completely changing the layer 2 forwarding path. In addition to that, you need to be fully aware of spanning tree protocol enhancements. Enhancements for performance and enhancements for stability. Now, if you're running rapid spanning tree protocol or multiple spanning tree protocol, the top two on this list are already baked into it. Uplink fast, backbone fast. Those are enhancements for the traditional, original flavor of spanning tree protocol. And they've just simply been baked into the newer, enhanced versions of it. But port fast, something you'll need to know. Now, when it comes to the stability mechanisms, we need them. They're an absolute must in any spanning tree protocol deployment. Why? You spent all that time setting up spanning tree protocol. You want it to be stable. You don't want it to be messed with. Why? Because it determines the layer 2 flow of traffic. So BPDU guard, BPDU filter, root guard, loop guard, all at the top of the list of stability features you want to know for spanning tree protocol. Some of the other topics you'll be exposed to include port security, DHCP snooping, and private VLANs, which are all security-related features. You'll also be exposed to SPAN and RSPAN, which is a packet capturing tool that is available on our Catalyst switches. Oh, and you'll also learn how to set up a multi-layer switch to perform routing and switching all at the same time. However, one of my favorite topics to discuss is related to first hop redundancy protocols, FHRPs for short. And this includes the hot standby router protocol, HSRP, the virtual router redundancy protocol, VRRP, and the gateway load balancing protocol, GLBP. What do these give us the ability to do? They give us the ability to have redundant default gateways. Why do we want redundant default gateways? Well, we're going to have PCs that point to a particular default gateway. If that default gateway goes away, who's going to forward on its traffic that has to leave the subnet? So by using one of these first hop redundancy protocols, we can have multiple default gateways, and as a result, if one of those default gateways fail, then the other default gateway can take over and continue forwarding traffic for the client out of the subnet. In our topology, we have DSW1 and DSW2 that can be the default gateway for VLAN 10. So what we need to do is we need to come up with this virtual IP address that's going to be utilized for HSRP. So let's set up HSRP here on DSW1 right now. Configure terminal, interface VLAN 10, and we'll say standby 10, IP address is 10.1.1.62. So here's the virtual IP address that the clients in VLAN 10 need to be configured with now. So we're no longer using the real IP address of that particular device. We are using a virtual IP address. And this virtual IP address is going to be shared amongst the members of the HSRP group. So right now, we're setting up HSRP between DSW1 and DSW2. So DSW2 needs to be configured with this virtual IP address as well for the same group, Group 10. As you can see, DSW1 promoted itself as the active forwarder. So let's go to DSW2. We'll go in the global configuration mode. We'll type in interface VLAN 10, which is our virtual interface. We'll say standby 10 IP, and the IP address was 10.1.1.62. And we should see here that DSW2 will detect the fact that DSW1 is already active forwarder, and it'll simply promote itself as standby. So therefore, it's on standby in case the active device fails, goes away, or the end station can't reach the particular default gateway. So what we want to do is we want to make sure that our client has the ability right now to ping the internet. So we'll go over to our client. Now on our client, let's issue a ping. We're going to say ping 192.0.2.1. And we're going to type in -T. This means keep pinging until I tell you to stop. So we can see right now we can reach the internet. We have connectivity. But let's bring down the link between ASW1 and DSW1. So we'll go over to ASW1. And on ASW1, I'm going to bring down that link, gig01. So interface, gigabit 0/1. And we'll say shut down. So we're going to shut down the link, which means that DSW1 and DSW2 will no longer see each other. And the traffic can no longer flow from ASW1 up to DSW1 to leave the subnet. And as a result, DSW2 has to become the active forwarder. So we'll just hit enter here, and then we'll jump over to our client and we'll see what's happening. So we'll see here that we're going to lose communication. A couple of packets are being lost, but we should have automatic failover here. DSW2 should now become the default gateway, and traffic keeps flowing. So wonderful feature. First top redundancy protocols. The example I gave you was a brief example of using HSRP, but definitely there are other options like VRRP and GLBP, which you'll analyze in the Switch 2.0 course. And that wraps up our sneak peek for Switch 2.0. We hope you enjoyed it, and we look forward to seeing you in a future session. Take care.